Okay, Pirates, this is our last topic for this unit. Last topic before winter break. Woohoo! Unless, of course, we've rearranged the order on this, but kept the video, in which case, last topic of the unit. All right. So, what we're going to do is we're going to look at a new concept called the Gibbs free energy, but more on that later. So, remember, what we've now done is we have looked at two different concepts for spontaneity, which may or may not be working together or working against each other towards spontaneity. So, for example, the first one that we learned about was enthalpy. And enthalpy tells us that if we have a high potential energy, systems tend to go to low potential energy or be exothermic and have enthalpy values that are less than zero. So the delta H, we want to be less than zero as it shows up here. We want it to be exothermic. Reactions that are exothermic are the ones that tend to be spontaneous. They just go. So if we were to just push this guy down the hill, right, he'll just go. He will not spontaneously go back up the hill, right? You'll have to put energy in to make that occur, but spontaneously speaking, you'll go from a high potential energy down to a low potential energy, exothermic. But we also know that the entropy is a factor. And in an entropy factor, systems tend to go from order to chaos over here. And if you go from order to chaos, then you have a delta S that is greater than zero or is a positive system. You have more chaos, more disorder. Well, what if you are in a situation where you are exothermic, right? You are going to go down to here, but you are going to less chaos. Well, what if you have a system that's endothermic, but you're going to more chaos? These systems that we have here can work together depending on the equation, but they can also work against each other. So how do I know what's going on? How do I do it? Well, a perfect example is that same one that we've been using all along, which is the Hindenburg. And what the Hindenburg tells us, the Hindenburg reaction at any rate tells us, combined with the idea of the second law of thermodynamics, which says that the chaos of the universe has to increase, we can actually take a look at all of this and understand what's going on. So if we look at this guy here, what really matters is that the disorder of the universe has to increase, right? But as we saw in our last segment, if I take two hydrogens and an oxygen, which are three gases, and turn them into two waters, which are gases, to two gases, three gas going down to two gas is actually a decrease in the chaos. So this reaction should not go, because it is becoming more ordered. The delta S, again, as we calculated it in the last video, right? We calculated the delta S for this reaction. It is negative 89. It is less chaos. The universe does not like this. It shouldn't be spontaneous. But we can do the delta H of the reaction, right? Well, the delta H of the reaction is negative 484. Now, that's a negative sign, so that tells us that it is exothermic, and so if it's exothermic, that should be like the ball rolling down the hill that's there, so that it should be spontaneous. But the second law of thermodynamics says that for this to occur, for a spontaneous process to occur, the chaos of the universe has to go up, and we are, again, quite clearly showing that we are decreasing our chaos. Okay, here we go. The chaos is decreasing, but remember, this is just our system. And remember that the universe is made of the system and the surroundings here. So the second law of thermodynamics says that for a spontaneous process to occur, we have to increase the chaos of the universe. Okay, well, hold on. So the universe has to go up. Now, our system went down. Our system went from 3 gas to 2 gas, so our system got less chaos. So I'm going to go ahead and put that number in here. The system went down by 89 joules per Kelvin. But what about the surroundings? Oh, hey, don't forget. not only did this guy here become more orderly, but he also gave off exothermically 484,000 joules, 484 kilojoules, right? So this guy gave off 484,000 joules. So it turns out that the surroundings, which are out here, the surroundings, they just increased by a whole bunch of energy. And assuming this took place at normal temperature, which would be 298 Kelvin, it absorbed 484,000 joules at 298 Kelvin. That's 1,620, positive 1,624 joules per Kelvin. So the surroundings went up by positive 1624 joules per Kelvin. Aha! There it is, guys. Check it out. The system went down by 89 joules per Kelvin, but the surroundings went up by way more than that, and so consequently, the delta S of the universe increased. And so consequently, this is indeed a spontaneous reaction. So, the second law of thermodynamics says that for a spontaneous process to occur, the disorder of the universe must increase. However, having said that, what I just showed you here is awful, is terrible, is a colossal pain in the butt way of doing these problems. We don't want to do things in terms of the universe. Sure, that's what the universe demands, but we need to work around this problem. I don't want to start doing all of these problems in terms of the universe. We want to do problems in terms of the system. That's what we care about. So how can we arrange all of our information so that instead of doing things in terms of system, surroundings, and universe, we instead just look at the system? Well, here's what we're going to do. If you want to walk through this, you can. The basic idea is that you're going to take the delta S of the system and the delta S of the surroundings and create delta S of the universe, except that we're going to establish that the delta S of the surroundings is the opposite of the delta H of the system divided by the delta T, divided by the T, and then we're going to go through and define negative T delta S of the universe as delta G of the system. If you didn't follow any of that, don't worry about it. You don't have to, and none of it really ultimately matters. If you really want me to walk through that conversion, I'll be happy to do it. The basic point is, if we want to cut right to the chase, is that this equation here. And what this equation here is, we've got a brand new topic. And our brand new topic is called delta G, the Gibbs free energy. And the Gibbs free energy is technically the energy available to do work, but basically what it comes down to is it combines all three factors into one equation, and it is one equation from only the system's perspective. So delta G is our attempt to take the enthalpy of the system, the entropy of the system, and the temperature of the system, and combine them in such an equation that tells us something about what is going on with the system relative to the universe. So this is the equation that you need to know, that the delta G of the system is equal to delta H minus T delta S. And what that means then is the following. If the delta G is less than 0, negative, then the system is considered to be spontaneous, or it's exergonic. Like exothermic, it's exergonic. If the system delta G is greater than 0, then it is going to be non-spontaneous, or it is endergonic, like an endothermic reaction, and it is going to be non-spontaneous. If the system is at 0, then it's at equilibrium. That is a discussion for another time there. So basically the idea is this. If the delta G is less than 0, then it will go. It's spontaneous. The reaction will go. If the delta G is greater than 0, if it's positive, then it won't go. It's not spontaneous. So that's how we can ultimately tell with these factors that are competing, is we take the H, we take the S, we take the T, we combinify them all together, and we look at it from one perspective, just the system, and we put them all together into this thing called delta G, and that tells us everything that we need to know about it. So let's check out a couple things here. First of all, here is our Hindenburg equation. Hydrogen plus oxygen goes to water there. So I get out my table of values and I do my delta H for this. Not surprisingly, the heat of formation of hydrogen is 0 and oxygen is 0 because they're elements that are in their standard states. And so, consequently, if I do products minus reactants over here, like I've learned in the previous ones, I get a delta H of reaction equal to negative 242. Now, I do the same thing, except this time I look up the S values. So for the S values that are here, I take this guy and I look up all of these guys and subtract all of these guys. Here are their S values, like we did before. And if I do all of that, I end up with a value of negative 45 joules per Kelvin. Fine, all good, nice and easy. And now what I'm going to do is I'm going to take this negative 242 and this negative 45, and I'm going to plug it into our equation here, which is this guy up here. I'm going to plug it into this equation. There's my delta H, there's my delta S. I'm going to assume that I'm at 298. By the way, I don't know if I've said this before or not. If I have, great. If I haven't, it's a good time to bring it up. If you ever see this little 0 up here, delta H of 0, or delta S of 0, or delta G of 0, you are talking about 25 degrees Celsius or 298 Kelvin. All right? That is standard temperature, 25 degrees Celsius, 298 Kelvin. Standard temperature. So that's what I'm going to use there. So here we go. So my temperature is 298, and here's my delta S's that are there. So I'm going to take all these guys, I'm going to plug them in. There's my delta H, negative 242. Then I'm going to subtract my temperature, 298, along with this. Please note, important thing for the math in this. Cannot stress this enough. Got to make these units work out. Please recognize that this unit is kilojoules. This unit is joules per Kelvin. And so if you want to combine the two of these guys together into the same equation, you're going to have to convert kilojoules to joules or joules to kilojoules for this to work out. So just be careful when you go to do this math. Excuse me. So I like to take my joules and turn them into kilojoules. So please note that it's 0.045 as compared to the 45 that's over here, because now it's in kilojoules per Kelvin rather than the other way around. So I do all the math on this, and I get the delta G of my system to be negative 228. So because it is a negative sign, because delta G is less than 0, it's negative. That means it is a spontaneous process. So that's the first thing that they might ask you to do. They might ask you to look at a system and do a delta G is equal to delta H minus T delta S situation going on here. But there's an easier way to do it. Why? Check it out. What have I got here? I am making 1 mole of an element, or 1 mole of a substance, and I am making it from its elements in their standard states. So if I were to do the delta G of formation of these guys, where I form them from their elements in their standard states, then that would have a value of 0, and that would have a value of 0, and therefore this would only be the value for the water, which means I could look up the delta G of formation for different substances. And if I look up the delta G for the formation of gaseous water, it would tell me that is negative 228, which is what I just calculated. So the point is that if we want to do this the easy way, and we want to know the delta G of a reaction, all I have to do is add up the products and the reactants of the delta G of formation, and those are, again, searchable in a table of thermodynamic values in your textbook or online or anything along those lines. And again, all elements in their standard states have delta G of formations of 0. So let's examine 2 different problems here, one of which is the long way and one of which is the short way. In sample 1, it says I have delta H of this and delta S of this. What is delta G? And again, please note I got that little 0 there. So that's telling me it's at 298 Kelvin. So what do? all I do is take my numbers and I plug them in. I get that delta G is going to be equal to delta H minus T delta S, or delta G is going to be equal to negative 182 kilojoules. And then I'm going to subtract from that 298 Kelvin times, now again, please note, this is in joules here, you see that? So I'm going to have to change that to positive 1.112 kilojoules per Kelvin. And now, what do I have here? I've got 298 at 0.112 is 33.4. So I got delta G is equal to negative 182 kilojoules minus 33.4 kilojoules, because the kelvins cancel out. And so then my overall delta G then is going to be 182 negative minus another 34. Oopsie. What was it? 298 at 0.112. Yeah, 33.4. I got that right. Okay, good. 182 negative minus a 33.4. 215.4. So this is a negative 215.4 kilojoules. And again, because it is a negative sign, the delta G is less than 0. This is a spontaneous process. So the long way of doing all of this is delta G is equal to delta H minus T delta S. The short way of doing it is to just look up their values and do products minus reactants. So if I was to look up the values for gasoline here and burn some gasoline, and I want to know what the delta G of this reaction is, it's just going to be the sum of the delta G of formation of the products minus the sum of the delta G of formation of the reactants. So what do I have? For my products, I have 8 carbon dioxides. So my delta G is going to be equal to 8 times negative 394. And then it's 9 waters. So that's going to be plus 9 times negative 229. So all of that is my products. 8 negative 394s and 9 negative 229s. And then I subtract from that the delta H's of my reactants. So I did him, so 16.4 positive. So 16.4 kilojoules, because the oxygen is an element in its standard state, so it's 0. I don't care about him. So that there then is my reactants that are going on there. So at this point, it's just math. 394 negative times the 8 is negative 3152. And then I got 229 negative 9 times, so minus 2061. Then I'm going to subtract from that the 16.4. So I got 3152 and 2061 and 16.4. Looks like if I've done my math right here, I get negative 5229 kilojoules for this. So unsurprisingly, the combustion of gasoline is an exergonic reaction. It is spontaneous. So the delta G of my reaction is negative. Put gasoline and oxygen together, give them a little spark to get over the activation energy, and the next thing you know, you've got yourself an exergonic reaction. Alrighty, almost done. Promise. Because the Gibbs free energy of a system is temperature dependent, depending on the signs of your delta H and your delta S, they could work together, they could work apart, they could do any number of different things, and the temperature might actually play a factor in whether or not the reaction is spontaneous or non-spontaneous. So let's take a look at what is happening here. Let's just say that I have circumstance number 1 here, where delta H is less than 0 and delta S is greater than 0. So what that means is that this is a negative sign, and then I'm going to be subtracting, again here, from that my T and my delta S. Now T is in Kelvin, so T is always positive, because again the T is in Kelvin, that's there. So If I have like this blue situation here where I have a negative delta H and then I have a positive delta S that's here, think about what that means. Negative delta H, exothermic. Well, the system wants to go to spontaneity. Positive delta S, less order, more chaos. It wants to go to spontaneity. Both of these guys are driving the reaction towards spontaneity. So because this is exothermic, you can say it is enthalpy driven. The enthalpy is helping. And because the delta S is greater than 0, you can say that this is an entropy driven. So both factors are helping on this particular case. And now look at the math. I've got a negative sign here, and I'm going to be subtracting what is the product of two positive numbers. So a positive and a positive is a positive. So I'm going to have a negative. I'm going to be subtracting a positive. That's going to make it even more negative. So no matter what the temperature is, this is going to be a negative delta G, which is why this is spontaneous under all conditions. No matter what, if your delta H is negative and your delta S is positive, it is being driven by both enthalpy and entropy. They're holding hands and they're helping this be a spontaneous process. And so consequently, it will always be spontaneous. The temperature doesn't matter. But what if we had a system like we had here in number 4? I'm going to jump down to number 4 here. Use a different color. What if I had a situation where it was an endothermic process, or delta H is positive? So this is positive. Well, that is not driven by the enthalpy. The enthalpy is not driving this process. So this is not enthalpy driven. Because to be driven by the enthalpy, you have to be a negative delta H. This is positive. So this is an endothermic process. It's not helping it be spontaneous. And then what would happen if my delta S of the system is less than 0? It's more order, or more to the point, it's less disorder, right? Well, think about that. That is not entropy driven, because the universe likes it to be more chaotic. So if it's not being driven by the enthalpy, and it's not being driven by, yikes, and it's not being driven by the entropy that's here, right? Then what's driving it? And the answer is nothing. It will never be driven. And let me prove it to you. If I've got a positive delta H, because it's endothermic, and keep in mind that I'm then subtracting the product of two numbers here. This is always positive because it's Kelvin. And remember, the delta S of the system is negative because it is going towards more order or less disorder. Then what happens when you take a positive and multiply it by a negative? You get a negative. And then what happens when you subtract a negative number? Well, it becomes positive. And so consequently, I've got a positive and a positive. So no matter what you do here, the delta G of the system is going to be positive, and therefore it is going to be non-spontaneous. It's not going to go. Because the entropy is not driving it, the enthalpy is not driving it, nothing's driving it. And so if nothing's driving it, it will never be spontaneous. And so consequently, this will not be spontaneous under any conditions, no matter what you do. So circumstance number 1 up here that I put in blue is delta H is negative, delta S is positive. Under this circumstance, it's always spontaneous. The one that I just did in red here, it is endothermic. That doesn't help. It is becoming less chaotic. That doesn't help. This is not spontaneous no matter what you do. Now I've got 2 more circumstances. What would happen if I'm helped by one but not the other? So circumstance number 2 here, I'm going to put in orange. It's exothermic. So if it's exothermic, that means I have a negative delta H. That's helping. That is enthalpy driven. Enthalpy driven. The enthalpy is helping that system go to spontaneity because it's exothermic. It's going down the hill, right? But what if it's enthalpy driven, but it's becoming more orderly? It's becoming less chaotic. Then you'd be subtracting the product of a positive negative over here. So you'd be subtracting a negative number, because a positive times a negative is a negative. Then you'd be subtracting a negative, and so it would be positive here. Well, wait a minute. Who's going to win, the negative or the positive? Now, what we've got is we've got a situation where the temperature is going to be the tiebreaker. If the temperature is going to be the tiebreaker, then it depends on what the temperature is. And in this particular case, it's going to be more favorable at low temperatures, whereas if we were to reverse it and make it be an endothermic process and have it be more chaotic, it's going to be more favorable at high temperatures here. So if it's enthalpy driven, it's going to be spontaneous by making delta H less than 0. If it's entropy driven, it's going to be spontaneous by delta S being greater than 0. Those two factors might work together. They might be against each other. It depends on the circumstances. Let's take a look at a problem. Because we can calculate the temperature at which this occurs. Remember our equation, delta G is delta H minus T delta S. If it goes to positive to negative, that occurs at 0. So I'm just going to take my delta G and turn it into 0. And then I'm going to rearrange the rest of the factors so I can actually calculate the temperature at which that occurs by rearranging this equation. Check it out. Here is an equation. Magnesium oxide plus carbon goes to magnesium plus carbon monoxide. If I just will go ahead and calculate the delta G of the system, it's positive 432 kilojoules. So it's non-spontaneous. But that is at 298 Kelvin. That's what that little guy here means. That's at 298. But might this guy be able to be made spontaneous? Well, check it out. I have solid and I have solid going to solid and gas. Ooh, the delta S for this guy should be positive. I'm increasing the chaos. So consequently, if I'm increasing the chaos, this is going to be an entropy-driven reaction. The entropy is going to drive this reaction because I am making more chaos. So there should be some condition that I can use to make this guy spontaneous. I just got to find out what it is. So I go to my textbook and I look up my delta H values, and I turn out that the delta H is positive 491. So it's not enthalpy driven. It's non-spontaneous, but we would have expected that. But it is entropy driven. If I check that out, it's positive 198. So again, I should be able to figure out how to make this guy spontaneous. How do I do it? Well, I plug it into my temperature equation. The temperature is going to be equal to the delta H divided by the delta S. My temperature was 491 kilojoules. My S, again, the joule kilojoule situation, I'm going to divide this by 0.198 kilojoules per Kelvin, and I get an answer of 2,480 Kelvin. So what that means is that if I can get the temperature up past 2480 Kelvin, then this reaction actually goes. It will actually be spontaneous, because if I can crank the temperature up to that point, then my entropy will be large enough to overcome the value of my enthalpy, and I will actually get the reaction to proceed. So our last equation here is this temperature one, where you can actually figure out what the temperature is of a reaction for it to be spontaneous or non-spontaneous, depending on what your enthalpy and entropy are. So the Gibbs free energy, going back to this, is the combination of all of our factors: enthalpy, entropy, and temperature,